have the pleasure of hearing Dr. Wulfhekel.
Wulfhekel.
And his expertise lies in the field of surface and physics, and with a particular focus on spectronics dynamics. And today he will give us a lecture about the scanning during microscopy and spectroscopy of thermal. So please,
Thank you very much for the kind introduction, and I'm glad to be here. It's my first visit to this part of the world. I was pleasantly surprised by the city. Not properly closed because it's so hot here. I just changed to shorts. But since my computer does not allow to share its keynote, now this camera takes this and it cuts my legs. No one sees me on the internet with shorts. Okay, good. Anyhow, I understood this is public, the recording, so I will be careful with some of the words and be less direct. Yeah, let me give you some words about my background. So, I was educated as a theoretical particle physicist in quantum chromodynamics. Went to Australia to do 1 year study there, and my supervisor decided to take sabbatical exactly at that time, and he was in the US. So very pleasant surprise. That means I started theoretical solid-state physics and also did experiments, and then I realized maybe experiments is more fun, at least for me. So I'm what you call a single-eyed person under blind when I'm talking to experimentalists, and I don't know the composition of this audience. Who is a theoretician? Okay, and experimentalists are roughly half-half. Okay, so I'm half blind, one-eyed, or whatever you think. So be generous with the stuff I'm telling you about theory. So this time I will have 3 lectures. The first one I will talk about fermions. That's the electrons actually that we want to see with STM. It's a microscope for electrons, electronic states. In the second lecture I will show you that you can also see bosons. And in the third lecture I will generalize the things to systems with spin. So at the moment no spins, no boson, just electrons without spin. And I start really simple. So I start with a historical remark, then something about how to calculate the quantum current, actually what we see, in what approximations. Then we have to talk about forces which are typically neglected in STM experiments. And then I go beyond the simple part. So K-space is also important. So we, of course, it's a microscope for real space, but we have access to K-space by Fourier transform essentially. And then I will go to a little bit wider aspects of the transform. I hope that you had some of the lectures already. So lambda optica, and make a distinction what we actually see. I will revise our first statements here, and then I quickly talk about superconductors. So at the beginning it will be really simple. You all know Wulf developed the scanning tunneling microscope. They are also involved in 82, and it was immediate success. So it's one of the rare cases where the Nobel Prize was given very shortly after this discovery. The main achievement is to get an atomic resolution on conducting surfaces. So they got $1 million for it, and to share it with the two. But what is maybe less known is there are 3 other gentlemen, Young, Ward, and Thor, that invented the topographer, and that was 10 years before, 72. And that is the STM. So it's exactly everything that is in STM. We have a tip here in front of the sample, bias voltage is in the tip of the sample. We can move the tip in x, y, and z direction, and there's what's called a feedback loop. So current is measured, and the z coordinate of the tip is adjusted so that the tunneling current is constant. So every time you buy an STM, they get money for the patent, and not the Nobel Prize winners. Now, why were these gentlemen not get the Nobel Prize? The main point is vibration installation. So you have your tip and your sample. I will show a movie of this, and you are really almost in contact. So the distance is, say, an atomic diameter, let's say, a couple of angstroms. And this system has to be stable mechanically. And you have to insulate it from vibrations. And the main point of the IBM group was a damping system that took away the vibrations. So you have to go down to picometer vibration installation, which is not an easy task. So this was the key to actually get atomic resolution. But in principle, everything was already in. Now, this is super simple, so this is just to get an idea how the tunneling gravity will depend on the distance. We take the simplest possible model, one-dimensional model. We have a barrier, we have two metals. The plane wave impinges the barrier. The energy of the particle is lower than the barrier. You get a tunneling effect. You have a Schrödinger equation. Join the wave functions here. And then you get a transmission, which depends exponentially. So this is not the exact form. This is approximated for low transmissions, which is 2L kappa over h bar. Kappa is the length. And so these energies, typically this is the Fermi energy, these two states, no bias at this simple picture. And the work function is this barrier here. Work functions are roughly 3-4 electron volts. If you plug in the numbers, it means this kappa is about 1 angstrom. So that means when you change the distance between those two electrons by 1 angstrom, you get 1 order of magnitude of translation difference. And that's gigantic. So we have an extremely sensitive detector for distances. That's the basic principle. You can ask any questions anytime. Yeah?
Do I understand correctly that you actually can measure only conductor? Or
yes, in what I will tell you now, you can only measure conductor or samples. I mean, thin insulators have also evanescent wave functions. So you can also tunnel through a thin insulator. But very recently there have been high frequency SDM, so I don't speak about that. So you modulate the voltage at megahertz, and then you get an also charge and discharge very quickly, and you measure the AC current, and in this way you can also tunnel on insulators. But for the time being, this is all metals. So this is the constraint that we are in, and I will show you that it's actually more complicated than just measure. Okay, so how does this look like? Now I show you, I have 2 videos, that's why I don't have this on PowerPoint or anything. So this is an SEM image of an STM tip, which tunnels here underneath the tip to a substrate, it's silicon, and there are lead ions on this. And the Z position is kept constant by the feedback loop, so this tip actually doesn't run into this bump, but the current is increased and the tip is automatically retracted. And if you go down the island, go sideways, then the gap becomes larger, the tunnel becomes too small, and the feedback regulator will actually put the tip closer.
and what is the size of the bomb?
This is very big. I mean, this is SEM, so I guess these are, the tip has maybe the end diameter of, let's say, 20 nanometers roughly. But you can also do it with TEM, transmission electron microscopy. Is it wrong? So, now this is from Tokyo Institute of Technology. You could look from the side now with the transmission electron microscope. You can see the tunnel barrier. This is the sample, it's crystalline. This is the tip, not crystalline. Okay, this is for some reason upside down in their video. You see these atomic distances. It's 3 atoms diameter, and now this is on the side how the tip is scaled. And it never touches the surface, so it only feels the wave function which leads between the two contacts. So it's a very mild technique. So typically you work a very low transmission, so like 1 volt, 1 nanoampere, that's a giga ohm. Point contact resistance is 10 kilo ohms, so that means the transmission is very low. and the wave functions hardly overlap.
Sorry, and how they film this movie? Like,
Okay, they really have the sample tip. We look from the side of the transmission electron microscope.
okay.
TEM, so on the plane waves, and optics. The other one was SEM, so the raster electron beam. But here you can see the atomic layers.
Yeah,
so
so
this is only a couple of atomic layers. What do we actually see in this here? So in our simple picture, it was basically topography. Yeah? So the distance in the vacuum is always the same, because the wave function falls down. But this, of course, is not reality. We live in 3 dimensions, not 1 dimension, and we have crystal structures, we have bands, with states. So the first answer was given by Baldin well before any SEM was actually thought of. It's this standard problem of tunneling. And it's solved like that. So we have, this is a picture I took from Naumann. So already tip geometry, but we have 2 electrodes. Both of them are considered solved, so the Schrödinger equation is solved. But you do it artificially. You separate the system into 2 parts. So you have the kinetic energy and the potential of the left part, and it jumps here at this boundary to 0. And the second electrode, again, you have kinetic energy and potential energy, and here the potential energy samples. So you separate the system into 2 systems. You know the eigenstates, and then you do time-dependent perturbation theory. So you have the sample always there, and you adiabatically switch on the tip and ask what is the tunnel rate. So this, I mean, the theoreticians will know exactly what was the answer. Yep.
Sorry, by adiabatically switching, you mean like moving those?
No, you have the tip here.
Okay.
So you switch on this tip potential.
I did the potential. That's okay.
Yes, this landscape, and then you ask what is the tunnel rate.
Okay.
And this is time-dependent perturbation theory. You know what comes out. So it's the rule, of course. So there are many states to integrate all the states energy. And you have energy conservation. So the electrons hop between tip and sample. Of course, they can only hop from occupied to unoccupied. So what is here is the difference in the Fermi functions. So if both are occupied, this is 0. If both are unoccupied, this is 0. Only if one of the 2 is occupied, the other is empty. And then you integrate over the states. So what you end up is the density of states, sample, and then you have a tunneling matrix element. So this is tunneling through a vacuum barrier. So this is first approximation featureless. It's the same for all electrons, which is not exactly true. But this matrix element can be computed on this imaginary separation line by the flow of the wave function. So it does not matter actually where you put this line. The separation line will always get the same answer. This generally is true for any Planar junction. And SFL it was calculated by Baldin, 61. So who knows Baldin? What, yeah?
PCS?
PCS. Something else? Yeah, transistors. So what makes Baldin special?
Everything.
The Nobel Prize.
2 Nobel Prizes is not so special, but
The Nobel Prize.
yes, it's the only person who ever got 2 Nobel Prizes on the same subject. So it's exceptional, and he solved many problems, but at those times, of course, the problems were easy to solve. Nowadays, it's not so easy to get any Nobel Prize anymore. Okay, but let's adopt this now, maybe more for our geometry. We make a constraint on the tip. Now, we want sharp images. So it's a good idea to have a sharp tip. And the idea of Tasman and Naumann was actually to take a spherical end of the tip and just in the far distance take an S-wave function. So this is the asymptotic behavior of an S-wave wave function. And if you then put this in and you integrate over this flow, I mean, I didn't do this calculation here. Oops, sorry. But you see, you can partially integrate and you have the Laplace on the other side. And the Laplace of the tip is the delta function of this. So actually, This evaluates the density of states of the sample exactly at the position of the center of the sphere. So under these very simple assumptions, it is just an S-wave function at the end of the tip. Our tunneling current is the integral. Now I go with temperature very low, so I from the Fermi functions, so I get a Heaviside function, and I get integration window only between the two Fermi energies. And another approximation is that this thing is only one atom at the end, so this state at the end will be short-lived. So it's not a block function which lives forever, but it's actually it will be very broad in energy. So it's not sharp in energy, it's very broad in energy because it's localized. Maybe it's a better picture. So uncertainty principle, this is very localized, so energy is very spread, and we just assume it does not depend on energy. This is not correct in all cases, but it's the simplest thing. Then you have some constants here. You have covered the decay constant we had before, but you see what in this approximation enters is the density of states. So that means we see electron density at the suspicious point in the center of the tip sphere. So you can calculate this. Now let's go from a localized to a relocalized picture. Now this is a picture in localized. We see just on DFT calculation, that's also done by Tesla, how the density of states of a metallic surface looks like. We see the atoms here, these dots. Close to the nuclei, the electron density is pretty high, and then it falls off. So this is exponential. It falls off very quickly to the vacuum. And we have relatively low conductance, so we sit somewhere here on one of these iso surfaces. And the SDM with the feedback control will take this kind of trajectories. If you want to express the local density here in front of the sample by bulk states, you have to consider that the bulk states will exponentially decay into the vacuum. Yeah? So there the potential landscape stops, the work function comes, and all the states exponentially decay. And so this decay, or this localized wave function here, consists of bulk wave functions. So I only put the block part, the plane wave part here. And this sample is translation invariant in x and y, but not in z direction. So our k perpendicular is not a good quantum number anymore. We have to integrate over it. And we only keep k parallel in this description. And then it exponentially decays in the vacuum, but it exponentially decays as function of k parallel. So the higher the k parallel, I mean, k parallel is the sideways momentum. So this is k parallel equals 0. And if I want to construct a plane wave which tunnels here, k parallel not equal 0, geometrically the path through the vacuum is longer, or you can of course do it correctly in quantum mechanics. And that is why the corrugation actually decays. The further you go out, the less corrugation you have. Now, on this line, there's only a very small change in z position when you fix the current to a constant density of states. While if you go very close to the surface, these iso density lines are have more corrugation. So this tells you, yeah?
How to read the plot?
This is position. This is x. This is position from the surface. At 0 is the last atom. And plotted is iso density lines for the electron density. So here it's 10 to the minus 3, and then it's 4, and whatever. I don't know what units. Electrons per square angstroms or something.
Okay, yeah. Okay, thank you.
So the wave function exponentially decays, but this exponentially decay also depends on k parallel. So if you have a low tunneling current or low tunneling conductance, you're going to this far out iso lines of the density, and your corrugation is bad. You don't see atoms basically. And if you want to go see atoms, you have to go closer. That means either increase the current or decrease the bias voltage. So, maybe I should explain this one. So this was tested Yeah, unfortunately, I don't have the citation anymore. I copied from a paper from Freeman. It's in some obscure journal and couldn't find it anymore. But these are just calculations, and the experimental observation, this was in tungsten, is roughly propagation of, let's say, 0.2 angstroms. And if you do the theory with S-waves, the S-wave tip, you are really much lower in propagation. So there was a discrepancy. And this is a nasty discrepancy, which was later solved by Wulf and also Stefan Bügel. So this is the lecture note from Stefan Bügel. I copied this, but there are also papers by Wulf. So if you look at the wave function of the tip, now, actually, since this dependence is so strong on the distance, only one item sticking out by 1-2 angstrom completely dominates the tunneling current. So actually the shape of the tip is not so relevant. So one atom will stick out somewhere and it dominates the tunneling current. And here you see this atom was chosen to be chromium, manganese, iron, lithium, palladium. And you immediately see the d electrons here. And the wave function is not necessarily spherical, but maybe directed, or actually less directed than we expect. And you can do the same trick. You don't take an SPD wave, you choose another orbital, and then the matrix element is not anymore. So an S is just the density states the wave function. Position R, if you have a px orbital, it's the derivative with respect to x, y derivative, y, etc. Yep.
So, do I understand correctly from these pictures that the characteristics length scale for the decay of the function is like less of the order of the distance between the atoms?
Yes, it's just it's very short range.
Okay, thank you.
And the standard approach is S-wave, and you get the density of states, but it's not always true. You can have also derivatives of the density of states. So this you should keep in mind in interpreting data. The standard interpretation is we see density of states, and that's kind of okay, but if you have very large correlations, you have to think maybe our tip orbital actually is different from the S orbital. Okay, good. Yeah.
If possible, could you please speak a bit louder, because
Louder? Okay, I try. Okay, on the back you cannot hear me. Yes, one solution is come to the front. The other is to remind me repeatedly that I should speak up. So I leave it to you to decide. Still, the agreement between STM images and the theory was not 100% convincing, especially on metals which are soft. So this is an example, again from Werner Hofer. There I found the citation. This is a low bias voltage image calculated in full transfer theory for copper. And you see the corrugation here is with the Z contrast. You see it's very, very small. And the observation is actually pretty big. And especially if you want to have atomic resolution, so that means you go closer with the tip. The answer is the Bardeen approach, that we solve the Schrödinger equations for tip and sample separately. If you bring tip and sample very close, is not a good approximation anymore. But the system now acts as a combined system. And you have two metals. What will happen if we bring a metallic tip close to another metal is that bond formation begins. And bond formation means forces. So under these severe conditions, also forces are there. And that means if we are on top of an atom, you try to build an atomic bond, and if the metal is soft, you will lift that atom a little bit out. And this increases the corrugation to values which are in agreement with STM observations. So it's not so simple. Yeah? So the simplest model you find in most of the papers is STM sees the local density of states, LDOS, the square of a wave function, but the tip might change this to a derivative, the forces might change this. And actually, you might think this is annoying, especially the forces, and the contrary is true. Because if you have forces between atoms, for example, and orbits on the surface, we can use this force. So at low tunneling conditions, low tunneling conductance, the wave functions don't overlap too much, there are hardly any forces, but we can tune this just by turning the knob on the STM to a higher current, approaching the tip, increasing the overlap, there's a force, attractive force for example, and then we are not actually forming the bond, but we are about to form the bond, and we can move the STM tip sideways and drag on as orbits. And that means we can build artificial structures. So we have a lithography technique at hand that can move any atom on the surface to any position. So it's an ideal quantum mechanical machine. We can play with things and construct wave functions, and there are many nice examples about this. Okay, so far this was imaging, and with the addition of forces. But it's always the integral over, at low temperatures, between the two Fermi energies. Can we learn more? Ah, sorry, I forgot one thing. They are not only forces. I should look on this one more often. They are not only forces, they are electric fields. So, let's say we are at one bias voltage 1 volt and we are 1 nanometer away from the surface. Then we have a potential drop of 1 volt per 1 nanometer. That's a gigavolt per meter. So these electric fields are gigantic. I mean, if you think about Stark effects in atoms or I don't know, these are megavolts per meter. Now we are gigavolt per meter. So a lot of things can happen. So first of all, a very often found effect is on semiconductors. On semiconductors, the density, the charges are low, the carrier density concentration is low. That means our conduction band cannot screen very well electric fields. We get band bending. So we park a tip in front of a semiconductor, let's say it's n-doped, and we have a positive voltage. We lower the potential of the electrons at the surface. That means we form locally a quantum dot below the tip and actually modify the density of states strongly. So that was a typical example. So if you look at semiconductors, keep in mind that screening is not very efficient there. You have band bending, and actually what you see is not the density of states of the uncharged semiconductor, but by applying this electric field, you would have band bending. And in metals, of course, yeah.
Is it possible to use semiconductor tip?
Yes, people are also using semiconductor tips. There is a very big project going on in Aachen where Markus Morgenstern actually even uses heterostructures here to amplify the tunneling current directly at the tip. So that's like a MOSFET, this is the gate, and the charges transferred to the tip will induce a very large current. And then you can get sensitivity to single electron tunneling events, which is actually quite nice. But semiconductor tips exist. Okay, good. So this was a metal tip in front of a semiconductor. And you know our metal screening length is very short. Typical metals have a screening length of an angstrom. So you expect no effect. And that was long belief until we did this paper here. It's already, oh shit, I'm getting old. It's already a long time ago. This was an example of iron on copper. Now I should say iron is a complicated material because it has two modifications, FCC and BCC. And BCC is the normal modification at room temperature, it's a ferromagnet, and FCC is an antiferromagnet. And they differ only a little bit by an expansion of the lattice. It's a martensitic phase transition without actually diffusions happening, just expanding one of the lattices. And if you look on an iron in two monolayers, two atomic layers of copper, you find BCC, hard to read, red BCC, and FCC areas. Here they differ in their density of states. So you can see it in contrast in the STM images. But if you apply a voltage pulse So we measure at very low voltages. This is hard to read, about 0 volts. And we give +1 and -2 volt pulses. The screening will now also affect these metals, although it's only an angstrom scale. It can switch. If I do the pulse here, I can switch BCC to FCC, and with another pulse with opposite polarization, I can switch back to FCC. So we can also change the modification of materials with that under certain circumstances in metals.
Is there something written on those pictures?
Yes, unfortunately, if I kill the light, it's better to see. There's a red BCC here, and there's a red FCC here. Or this island here is almost all BCC, and after the pulse, it's completely FCC.
Okay.
So that's
So you can induce magnetic transition
Yes.
this way.
yes.
And
So
like-
there is, of course, magneto-electric coupling, but due to electric field being a polar vector and magnetism being actual vector, I cannot switch the direction of a magnetization, but I can switch the size of a magnetic moment. So this allows me to switch on and off ferromagnetism.
By pulse, you mean actually changing the potential?
Yes. So this is very small. I will put the slides online, but you see the time trace here. And I give like 1 point something volt and -2 volts. After each pulse, my structure changes.
Wow.
So STM is a very brutal technique. And so you always have to keep it in the back of your head. If you interpret your data, your experimental data, are there traces that I actually modify my state? I want to test by the observation, by electric fields, by currents, by overlaps of wave function, etc. pp. So one has to be a bit careful. Okay. So let's go to K-space and to energy resolution. So this was a formula under assumption of very low temperatures, small overlap of the wave function, constant chip density of states. This is of Hamann. And if I take the derivative of the current with respect to the bias voltage, it's only the upper limit of the integral, I get the best information, that is the local density of states, now energy resolved. This is like the dream of any person who does quantum mechanics. That's the square of the wave function of this energy. So we can map wave functions. But how do you do this? I mean, I can only measure the current. I have no instrument that gives me the derivative of the current with respect to the bias voltage. So the standard is to do an IV curve. I is U, and there's some kind of structure, and my local density of states and the slope of this curve. So you can record this and do a numerical differentiation. And of course, our current has noise. So in reality, there's noise also. And the simplest way would be to integrate. Yeah, we measure the slope here precisely by repeating the measurement over and over again. But that means we look at the zero frequency Fourier component. Yeah, so you measure the slope very precisely, for example, going very slow over this, averaging very well. But it means we do the Fourier component 0. And that is a very bad idea. Why? So if we have current and we have frequency, we have the shock noise, which is constant. But all of the technical instruments contain one of the F noise. Yes, so you have variations in your amplifiers. Some atoms are rearranging in your transistor, and this actually explodes. So if you average very long, it means you pick this Fourier component here, and it's the most stupid thing you can do. So instead, what you do is you take U0 plus delta U cos omega t, modulate the bias voltage, and then you got to modulate the current, and you demodulate this frequency omega. So we shift this averaging away from zero frequency to omega, and you can pick a particular omega in your experiment where your machine is not noisy. So what we do is we add this delta U cosine omega t. Omega t. But this means our resolution is limited by this modulation. And there's also another limitation of the energy resolution, which comes from the fact that we are not at t equals 0. Our Fermi functions are smeared. And we actually have a convolution of two Fermi functions. And if you convolute them, they almost look like a Gaussian. So here, all the states are occupied. Here, all the states are empty. And in this region here, they are partly occupied and partly empty. And the width of this can be, so the exact shape is the sharp one. And the Gaussian fit is 3.2 kT. So our resolution, spectral resolution, is given by 3.2 kT square. It's smearing due to the temperature and 2 delta U effective. So U effective is 1 over square root this delta U. So this limits our energy resolution. It's actually worse than photo emission, because we have this Fermi function of the chip on top of it. And with Kb equals 86 microelectron volts per Kelvin, you can do the calculation. At 4 Kelvin, we have 1 milli-electron volt resolution. 1 milli-electron volt is good, but not good for many specific problems. Yeah, if you think about superconductors, 1 milli-electron volt is a gigantic energy. So if you do spectroscopy on a superconductor, you have to go lower in temperature. So you notice here, I just took the derivative with respect to EU here, but there's a kappa. Kappa is the transmission coefficient. Yep.
The resolution, you mean?
Spectral resolution.
Spectral resolution.
Yes.
Okay.
Spectral resolution.
So you're talking about different like Fourier components of the rho itself, right?
So this formula is general, yeah. Opala. Going up. This comes from thermal population, and then if I use this trick to reduce my 1 over F noise, I get a penalty, which is the modulation voltage. Because my average here is linear. Actually, this averaging function looks like a half sphere because it's cosines t. So it looks exactly like this. So this is the probability of U. And this is U naught, this is plus delta U minus delta U, and this width here is 1 over square root.
What is the typical omega which you use for this modulation?
So in the beginning of STM, these were IV converters with bandwidths of a kilohertz. Now we have IV converters 100 kilohertz of bandwidth, so we like to go to a higher frequency, which I should warn the experimentalists here is there's also a capacitance. Chip and sample they are a capacitor, so you get also capacitance charging. But the nice thing is this current is 90 degrees phase shifted to our tunneling current. Yeah, the tunneling current depends on U, and the charging current depends on U dot. Yeah, so we get a capacitive charging, current I capacitive, and I tunneling, and they are 90 degrees. So if you adjust your phase for the login, you lift the tip a little bit, and there's no tunneling current. You maximize the signal, and then you rotate it by 90 degrees, and you have the tunneling current. Technical things. Okay. So this was the formula here, but this kappa is a function of the bias voltage. Why? So in a simple one-dimensional model, this was the kappa, the decay constant here. If we bias the junction, it looks like this. So this is the potential at the beginning, the barrier, and the potential is skewed. So these electrons, they tunnel here, actually see a varying barrier, and the transmission becomes larger than expected. So you need to correct for it. So in principle, you have to be careful. There's a transmission probability, which depends also on voltage. It can be approximated by half of the bias voltage here, so it's the average barrier of this spatial dependent barrier. And then the derivative contains three parts. The part that I discussed before, this is the sample density of different states. Then we have the chip density of states, may also vary. Okay, we skip this. And usually we skip this transmission dependence. So this barrier typically is 4 electron volts here. If you apply a volt, you already start to see this change of the transmission probability. It looks like this. It's an exponential function. And if you want to correct for that, you have to take it into account and fit it. So let me give you examples. We want to measure now density of states. So simplest example is an old one. Reference is given here. It's a lead island. I give this example because in the second lecture I will speak a lot about lead as a superconductor again. It's sitting on copper. And copper 111 actually has along the 111 direction a band gap, partial band gap. I will speak about that also. Lead not. So these lead states cannot lead into the vacuum, they are reflected, but they can also not enter copper because there's a partial band gap in this direction. So they're bouncing back and forth. So the electrons tunnel from the tip into this thing and bouncing back and forth like a Fabry-Perot interferometer. Eventually they go out. They have some lifetime. So what we expect is these Fabry-Perot peaks here. And exactly this you can see, depending on the thickness of these layers, you can see these quantum well states. And if you just take this band structure, these are the dots, experimental one black, infinite square well is open symbols, they agree pretty well with these peaks. So these are quantum well states confined in the z direction. And this chapter is about k-space. You will kind of start to see where this thing is going. This is the thing, a property from k-space. So the electron has to travel from the top surface to the bottom, is reflected, comes back to the top, there's an interference, and these are standing waves, simple words. We will come back to that. Now, we can map now wave functions. So, as I said, total current is the integral of all wave functions in the energy window, simplest picture. And if you take the derivative of this with respect to the upper boundary of the integral, you get the wave function. And now these are examples. These are molecules. Same molecules. And there's a little tiny image here. This is the IDV spectroscopy. So you see a peak here, which is the lowest unoccupied molecular orbital, and a peak negative, which is the highest occupied molecular orbital. And you can set now your SDM to this bias voltage and record the IDV as function of position. And this is the SDM images. This is the HOMO, this is at the gap, the LUMO, and these are the orbitals from DFT. And you see, it looks pretty good. So, indeed, in the IDV, which is proportional to the localized density of states at this energy, we can map wave functions. This is an example I shot myself. So this is the copper. This is the Fermi surface of copper, and this is the copper 111 surface. So we sit here in the band gap. So this is the projected density of states. Now I collapse all this. Kz is not a good quantum number on the surface. We collapse everything. K parallel is still a good quantum number. So you squash this Fermi surface. So you get a hole which goes through, which you can see here. And all of these are projected light bands on the surface. And there's this gap in here, and then electrons can live in this gap because, first of all, Fermi energy is here, so they should be occupied. They cannot enter the crystal in this direction because the copper has no bands there, no states. And they can also not enter the vacuum, so they form a two-dimensional electron gas. And this is such a picture of the two-dimensional electron gas. I plotted the IDV as function of position. And for some reason or another, I have a dirt atom here and a dirt atom here. Now this two-dimensional electron gas, where I fix the energy by the upper energy of my bias voltage, and I measure the IDV, I can see the wave function of this two-dimensional electron gas being scattered from these defects. And it looks like a textbook image, yeah? So you can see that this is round, so I get just round scattering waves, and there's another defect here, they even interfere, so it would be exactly the solution if you would just do a two-dimensional scattering problem. You can map it directly with the instrument. One reminder is how to do the feedback. So I said that you regulate the tip so that the current is constant. This means you put the tip at a distance such that the integral over all states between 0 and the bias voltage is a constant. And you want to map states. And this is a contradiction. So I partly regulate away my states. Let's say I have just one state in this energy window, then my current is totally given by this one state, and then I make a derivative under the restriction that the total current is constant. I don't see the state. The example is here a very big molecule, also done in our group, where we record the IDV with a login. So we modulate the bias voltage during measurement and record the IDV as function of position, but the total current is kept constant. We get this object here. The alternative is to record the IDV at a constant height. So now we switch off the feedback loop and take away this constraint that the current has to be constant. That means we go horizontally over the surface, and that is the condition to really see the wave function. So in this case, you see the real wave function. And this is a convolution of the wave function and the total current. So here you have to be careful, and this is a big problem in the thing I want to explain next, quasi-particle interference. If you are not sure about your states, so the current is set so that the total current is constant, so the summation of all states, and the IDV looks only at the states at a certain energy, then if there's just one state, you're killing you the IDV signal. Is that understood? It's a little bit complicated. So I have just one state. So I have just one state, and I now have my tip here. Current is the integral over everything. Let's say my state is here. Yeah? In this energy window, this is my state I want to image, and the only state which is there is this state, so the total current is given by this state. And then I make the IDV. If I change this upper boundary, I get no C. Yeah? So it only works if I have many states, and then I can go out in one more state that will change my differential. But if there's just one state, I kill it by the feedback mechanism. So that's also something to keep in mind. But it's a detail for the experimentalists. We want to go to case space. So we had an example of this Fabry-Perot interferometer. Can we do that laterally? Okay, now I really need to kill the mice. So hold on. This one is big. It's better, you can see something?
Yes, we can see two red lines.
Okay, good. This is an atomic step. Lower torus, upper torus. You see a little bit of stripes here, and this is the IDV. So I make a map of the IDV. Yeah,
Oh,
much better. Yeah, you see this is an atomic step. Taken at a certain bias voltage, this is the IDV. And you see these lines, and here is a defect, you can see the scattering wave. Now this scattering is not going vertically, but now it's going sideways, and this is actually again the surface state. So this was copper. So actually the electrons tunnel into the system, and this two-dimensional electron gas, they can travel to the step edge, where they are reflected and come back. So you can see the standing wave pattern here. And you can measure the distance of these, or the wavelengths of this wave as function of energy. And from it you can construct a dispersion. And this is the dispersion of the electrons. Well, of course, there's a factor 2 because it's the square of the wave function and the forward and backward traveling one. But you can nicely see the dispersion. So you can do what photo emission can do, but you can do it for occupied and unoccupied states and local resolution. And you can model the decay. So you see this one decays the further you go away. Why is that? First of all, it has to do with energy resolution, but the second most important point is those states don't have an infinite lifetime. So if I go far away, there's a chance that my particle disappears into a byte state. So this interference pattern dies out with distance. And you can measure this dying out, and from this you can construct the lifetime of the states. These are the measured data points. And this is 1 over E square. This is Fermi liquid theory. So you see, this looks pretty nice. This is a Fermi liquid. And indeed, in a double exponential figure, you can see this slope here is proportional to 1 over E squared. So the particles with very low energy live very long. The particles with high energy scatter all over the place, and electron scattering is happening here. And they decay. Can we do better than that? Of course, the answer is yes. Let's just take statistically defects on our surface. So we have a statistical distribution of scatterers. So statistically means if I Fourier transform this, I get white noise, a constant. Fourier square of this point defect distribution gives me a constant. But every particle defect gives me a scattering wave. And what I see then, if I Fourier transform this differential conductance map, I get see a nice ring here. And it's actually with a diameter of 2kF. So you directly can map the Fermi surface. But be careful, what you see here is a forward wave and then scattered and come backward and interfere again. So actually it's a joint density of states of 2 propagators going in one direction and back. So this joint density of states is the real part of the Green's function times the imaginary part of the wave function plus this momentum transfer, and then it's proportionally the L-dose square. So you get a convolution of the spectral functions, and what you see is basically the nesting. So this peaks is nesting vectors of the Fermi surface. So you don't directly see the Fermi surface. This would be a circle with kF diameter, but you see the correlation, the joint density of states. So you need to deconvolve it to actually really get the dispersion. But in principle, STM can by this measure dispersions. So not only real space, you Fourier transform it, and you get everything that the theoreticians can calculate.
So B is the Fourier transform of this current, or what's that? So how was picture B obtained?
B is the Fourier transform of
Of this picture.
So it's the autocorrelation function, the square of the Fourier transform, is to be precise. So it's the autocorrelation function. This is also the autocorrelation function. Okay, good, wonderful. We have a very powerful technique. We can see wave functions, we can Fourier transform, we can measure dispersions, lifetimes. Super nice. But everything was based on the model that the transport comes from the tunneling junction. My current detector is not at the tip or directly at the surface where I have my tunneling junction. My current sensor is somewhere far away. Is there a difference if I look at the current? And the answer is yes. And the answer, at least on the scale of the ballistic mean free path, is given by Wulfhekel in this theory. Did you have this transport theory? I saw it. Yes? Okay, good. So it's very simple. It's scattering theory, and the number of particles is conserved. So these are unitary scattering matrices, and then conductance is given just I. It's the sum over going from I to j, and the bias voltage difference. So if we have a three-terminal device, particles can go from 1 to 2, from 1 to 3, or back, depending on the bias voltage. Why am I talking about two contacts? Am I stupid? No, these experiments have been done. So let's take now the tip, a base, and a collector. The base is metallic, the tip is metallic, the collector is a semiconductor. And a bias, this junction, so this is the band gap. If the bias is small, electrons will tunnel through. They cannot enter the collector because there's a band gap. They will flow through the base. But if I have a bias voltage which is larger than the band gap here, then part of the tunneling electrons, which have enough energy, can actually go ballistically through the base and be collected in the collector. So we can do an experiment where we have two currents, a tip, a vacuum, semiconductor, and a collector. Base. We have one, so we take the total current here, and then this is the ground, and this is the collector current here. And indeed, if you ramp up the voltage, nothing happens, nothing enters the collector until you reach the height of this barrier, and then part of the current goes ballistically through. So it's a three-terminal device now, and we have split the current into two paths. One is a high energy path, the other one is a low energy path. And the interesting thing is with this you can look through everything. So if there's a defect here on this barrier, you can see it in the beam current, although it can be hundreds of nanometers away from your surface. Just because those ballistic lengths are long enough. Yeah?
Sorry, so what is the role of the semiconductor on the right picture?
It's an energy filter. So if I have a small bias voltage, then they cannot go through the Schottky contact.
Yes, so on this picture, this is actually...
this is the situation here.
Yes.
And if we increase the bias voltage above the band gap, part of the current actually goes through.
Yes. I mean, I look at the left picture and I want to see on this picture the semiconductor itself. So
this is the semiconductor.
This is the semiconductor. Okay.
This is the collector current.
Yeah.
The collector is actually behind the semiconductor.
Okay, I see.
So we inject carriers in the conduction band, they go through and are eventually collected by the collector.
Okay.
So that means we have to be a bit careful. Currents are not only given by this tunneling matrix element here, but we have to think what can happen with the electrons afterwards. This will be a very central thing for the next lecture. But Landau-Büttiger also gives you something. Top, that is noise. So the classical shot noise are plotted already here. There's a noise density which does not depend on frequency and is 2e times the average current, or is 2e g naught. Times the transmission. But now the shot noise is not classical. We have fermions. We have to keep this into account, and this was done by Büttiger in this paper. And there's a correction going from classical particles to fermions is that the noise actually becomes proportional to Tn times 1 minus Tn. Why is that the case? So the shot noise comes from the fact that we are able to localize the electron. So the electron is on the left electrode and it jumps to the right electrode. This is a discrete jump. If the transmission probability is 1, you have an extended wave function. So actually, you never know where the electron is in the first place. Nothing jumps here, it's just the flow of the wave function. So if transmission is 1, the noise should disappear. And this is this correction. So if Tn is 1, the noise becomes 0. If Tn is 0, there's no current, then also the noise is 0. So this is a quite important thing, so you can measure that. It's a little bit complicated, so you have to split your current into two paths and separately amplify it, because all amplifiers have their own noise. So the current itself has noise, and the amplification has noise, but so you amplify it 2 times, and then you make a correlation on the 2 noises. So if noise peak, a click in the detector only comes in one of the 2 channels, this click comes from the amplifier. If they come at the same time in both amplifiers, this click comes from the tunneling electron. So you can actually analyze this noise, and this is the, oh sorry, I forgot the excess noise. Oh, excess noise. Where the heck is this going? 6. Fano factor. Fano factor. Okay, the Fano factor is here. So this is the classical noise, this is the quantum noise, and the difference between them you can express as a factor. This is the Fano factor, and so this is this excess noise, the Fano factor. And if you are with very low transmissions, it goes almost to the classical value, but if your transmission comes to 1 quantum of conductance, your noise disappears in this experiment. And then you can go closer with your tip, so actually that maybe 2 atoms will touch, you get a 2 atomic contact, the conductance becomes 2, you again go to this low noise. So by this you can actually learn about how many channels are in your experiment sometimes, because the conductance is the sum over all channels, and the noise is a different formula, and you can get out maybe how many conduction channels are actually active. And this noise actually is also very interesting. If you think about it, so you have single electrons that are, if the tunneling probability is not very high, that are either localized in the sample or the tip. And in the process, they quickly jump across the barrier. Okay, the tunneling time is a difficult concept, I don't want to talk about it. But classically speaking, there is a charge going from one side to the other. It's a time derivative of a current. It's a discrete current. It makes a spike in the electric field, and this electric field variation, because the tunneling current was there, changes the voltage in the tunneling junction for a short moment. And it's a dipole antenna, so you can also emit photons. So this is an experiment where the tip was ramped towards the surface, and the conduction was measured, going from 0 to 1 here. And at the same time, the camera is looking at the SDM junction and detects the photons. Now this noise of the charge will give you fluctuation in the electric field, and that means photons are emitted. And so this is the frequency of the energy of the photons, and this is the spectrum. There's a peak. This is basically a plasmon. And you see the energy of the photon. This is the energy of the tunneling electrons. Everything is fine below here. But under certain conditions, the photon energy exceeds the energy of the tunneling electron of the bias voltage. So it cannot be a single electron process. And actually it comes from the noise statistics. If you would Fourier transform the noise, then you can get from this, you can calculate the photon yield, and then you can see how this should behave. And this is for smaller EV, so this is the single electron process, this is the double electron process. And you see that also photons with higher energy than the single electron can provide actually in this time trace get noise at higher frequencies. So keep in mind that at these bias voltages you also create photons. And the current actually has a time structure. Okay, I should hurry up a little bit. I have too many. I don't need to hurry. Everything I miss now, I bring tomorrow. Important is that you bear with me and ask questions. So far, we described everything as density of states. And unfortunately, this picture is insufficient. It was so nice what Bardeen calculated, but he did an assumption that my electrodes are not changed by the current. And if you think about it, if there's a current, I will populate charges on one of the electrodes. Okay, this might be not very important because my electrodes are very big, so they go somewhere, I don't mind. But if the sample is small, they play a role. So I showed you this graph, this was the pentacene molecule, and if you calculate the density of states, this is the LUMO, and this is the LUMO. This is a charge-neutral excitation by a photon. This is the standard definition of LUMO gap. It's a charge-neutral excitation. So the optical gap is around here. I just translated this optical gap. It's about 2 electron volts. And the differential conductivity has these peaks here, here. So this is the LUMO, and this is the LUMO according to STM. It's wildly different. Why? Well, in STM we don't charge neutrally excite the system, but we physically add an electron to the LUMO, or we take away an electron out of the LUMO. So it's the addition or subtraction spectrum. Strictly speaking, it's not the density of states. There's a difference. So the density of states is as it says, is a number of electrons, a number operator.
Excuse me, could you repeat what is HOMO and what is LUMO?
Okay. Highest occupied molecular orbital, lowest unoccupied molecular orbital. So you fill the electrons into this molecule, and typically molecules are chemically happy, so all of the bonds are doubly occupied. So there is the highest molecular orbital with 2 electron population, and the next one is empty.
Sorry, but about what kind of molecules are we speaking about? I mean, like before that, I thought that we have this lattice and stuff.
Yeah, this is
how
about.
can we actually like focus to the single molecule, which is probably floating somewhere around? No.
No, this is a molecule on the surface, and I showed you the whole LUMO. It
Yes.
works very nicely, but the energies don't agree.
So they're like stick to the surface at some
They are
specific.
stick to the surface,
Okay.
so actually you can have. I mean, I can't make a contact to a single molecule to get out the current. So they are on the surface, but this might be a small thing only, but I want to highlight it because we need it later. So don't forget that in SDM you don't measure the spectrum of the states, but you measure the addition or subtraction of the spectrum. You really put an electron, you take out an electron. And the difference is the Coulomb charging energy. So this is not an experiment I did myself. I could take many other references here. But these are iron islands, the small white dots. They live on an insulator, 3 monolayers of iron, MgO, and then on iron. So these are small capacitors, if you like, plate capacitors. And although there are a density of states, I cannot populate these states because if I transfer an electron, I have to pay the charging energy. The charging energy is E squared over C. So these are actually separated by the charging energy. If you calculate the density of states, this would maybe be very close to states, but actually we don't measure these states, but we have to add or subtract them. So only if in between the 2 Fermi energies there's a discrete state, I can actually, so this would be the equilibrium state, I can add 1 electron here and it jumps off here. And again, add 1 electron and jumps off here. Here I cannot add this electron to the state because it's out of the charging window. So if I do the experiment, the IV curves don't look like density of states, but they have these gaps here. So they are steps. And in each step, if I ramp up this voltage, 1 more of these discrete charge states enters my energy below, and I get these steps here, or differential conductivity. It's very peaked structure, which has nothing to do with local density of states. This is really an addition or stretch spectrum. Now, if I have a big sample, to add an electron costs so little Coulomb energy that I typically can forget it. But if the sample is small, it's a small island on an insulator, so the charge lives for some time on the island, I have to keep it in mind. But let's go to really low temperatures. Let's go to millikelvin. 15 millikelvin experiment, Max Planck Institute. This is asked. This is just on a normal metal. Tunneling to a big sample. And what do you see? There is some dip at the Fermi energy. Why the heck is there a dip at the Fermi energy? It seems like we can't put a charge close to the Fermi energy. There's a charging energy. Well, I mean, the sample is so big, there is no charging energy on the scale. What this is so-called dynamical Coulomb gate. So, in this simple approximation, we see the density of states. So, we tunnel from a state from the tip to the sample state. Now, at a very low bias voltage and very low temperatures. So, this state has a lifetime. And the lifetime is proportional, 1/tau is proportional to the energy square from Fermi liquid theory and thermal processes. So if I go very low, I can forget these. So my lifetime explodes when I go to the Fermi energy. So if I'm at really low temperatures and really low bias voltages, I can tunnel with an electron, but then the state is occupied. And it takes a long time before this relaxes somewhere in my sample. That means the second one cannot enter for some time. And only if the energy is high enough, the time scale of my current, so the rate of the tunneling rate is, if the relaxation rate is faster than the tunneling rate, I don't see any of these, but if this relaxation rate is smaller than the tunneling rate, I will see the dip at the Fermi energy. This is not a density of states dip, this is what is called dynamical Coulomb gate. You find that very often. You still with me, or are you getting tired?
Especially with the lights.
Oh, I should put the lights there. I have no my images.
I mean, I would rather ask some very general question
Yeah.
about where are we moving actually to. So, like, you told about the STM, and you just show now some like special cases which
Yes.
can occur. And
Yes,
this is the
so
point.
it is
So
like
it is just like to get an intuition. Okay.
yes. So
Okay.
it's more for the experimentalist, if you like. So what to keep in mind? Where are my limits of my models? What do I have to consider?
Mhm.
Yeah, for example, energy resolution,
Yep.
charging, and not measuring density of states.
Mhm.
I actually measure the addition of subtraction spectrum. I can have Coulomb blockade. I can have dynamic Coulomb blockade.
Okay. Okay.
But also, maybe for you theoreticians, that there is something which can be measured, like noise. I can measure transmission function. I can measure lifetimes of the quasi-particles this way. Actually, quite interesting.
Would it be correct to say that this previous comment about on previous slide
Yep.
that here this dip is controlled by interaction between electrons?
Yes, or phonons. You have temperature. Yes. So at 4 Kelvin, you hardly see any of these. But at very low temperatures, in good metals, you start to see it. Yeah?
It also depends on the tip shape, right? The capacitance.
That's more complicated. There are also things that depend.
Even if you have an image charge in the tip.
P of E theory, you mean? Yes, I don't. I mean, this is enough. So there's no superconductor here, but if you're on a superconductor, then you have to be more careful. Then P of E is more. But this is really only for the specialists. But let's go to a superconductor. NIS tunnel. That's only a few slides to go. So, BCS superconductivity, a gap of 2 delta opens, as you know, and single particles can only tunnel into these quasi-particle states outside the gap. Very simple. So we expect the BCS, density of states, differential conductivity when you measure it. And that's actually what you get. This is measured by our instrument, not quite as cold. This is only 25 millikelvin. But these are unpaired electrons. So in principle, you expect this to see local density of states, convoluted with the Fermi-Dirac distribution. The nice thing is the Fermi-Dirac typically is much narrower than this separation here, so actually it drops out. And what you see is only a little bit of smearing here at the bottom and a bit of rounding here when you actually come with the Fermi energy across this quasi-particle peaks. But there are no thermal excitations of electrons and holes across the gap. So it's a simple convolution of this Fermi-Dirac function and our superconducting density of states. And that means from this you can get the deviation from the ideal BCS. And that gives you an idea of how good your temperature actually is. So our system works at 25 millikelvin. If you fit this, you need a temperature of 82 millikelvin. And this is the so-called electronic temperature. So our lattice temperature is given by the thermometer, but our electrons not necessarily are at the same temperature because they need some, to equilibrate they are driven, and our wire necessarily comes from room temperature where the Fermi-Dirac distribution is very smeared and it has to cool down, and this does not work arbitrarily well. But this is already actually quite a good number.
Sorry.
Yep.
That's one question. So before when you were talking about noise and your resolution, this was at the higher temperature, not
Yes, now we go really to low temperatures and the modulation. So this, for example, was done by numerical differentiation. There is no modulation to kill this. But you can modulate with a microelectron volts, no problem. You get nice signals when you're pretty cold and you have these sharp peaks. That works. But I just wanted to mention that your thermodynamic temperature is not necessarily the electron temperature. Yep. This is the dyne spin, so you have a lifetime of the quasi-particle. Yes, if I put 0 dynes, my temperature goes up. But of course, then the shape does not fit. Okay, good. But we can go a step further. Superconductor tunneling. Okay, if we are single particles tunneling, then we need to bias the junction by 2 delta until it starts. But if we are at 0 bias, I can tunnel with Cooper pairs to Cooper pairs. Now, this of course requires 2 electrons to tunnel, and both of them are exponentially suppressed in the tunneling process. So this actually scales with the transmission probability squared. So we have to go pretty close to it. But then you see a peak which is exactly at 0. And these are not thermally smeared. So they have no smearing. So what we now see is only the noise on our bias voltage. So we cannot adjust the voltage exactly at 0. And this one is already something like 80 millikelvin or 69 millikelvin. So that means this one is not really a Fermi-Dirac distribution, but it's our inability to actually set a bias voltage absolutely constant. So all of the electronics, if you say I want to have a certain voltage, will create some noise. And the third one is this condition, which is a play of reflection. I think there will be something, or there was something, I don't remember. But let's go close to the surface now with a normal tip. So normal superconductor. And we are inside the gap. So single particles cannot tunnel. But I could, in principle, how does it do? A tunnel with one electron in a hole is free to reflect it. So I effectively a tunnel with 2 electrons, unpaired electrons, that are above and below the Fermi energy and create a Cooper pair in the superconductor. So it's again 2 particles tunneling, and this works for all bias voltages in between the gap. And now this has, of course, a charge of 2e. The conductance is larger. So this is down here in the gold niobium contact, which is point contact. So above the TC, there's a conduction of 1 G naught going through this junction. Now we go superconducting. You see somewhere in between the gaps, our current goes up twice. So two Cooper pairs now go through the junction. 2 electrons form a Cooper pair. And this is an Andreev reflection, so I will need that later also. Last foil. Can this be used for anything? It's a very recent example, so 31 science paper that I find particularly interesting. Why not combine our noise measurement with tunneling into Cooper pairs? Why is this interesting? If I tunnel into quasi-particle states, 1 electron is tunneling. And if I have something like Andreev reflection or Cooper pair tunneling, Joseph's occurrence, 2 electrons are jumping. So in principle, I can check at a certain energy range, are my quasi-particles single electrons or are they Cooper paired? Because here the noise is twice as large because the charge is twice as large. So in this case, I have single tunneling events of single electrons. In this case, I have only Cooper pairs tunneling. And if you measure this noise, function of bias voltage, for voltages below delta, so this is the integral noise density, where the charge is 2e, and outside the gap is 1e. Or if you like, as function of energy, the effective charge can be determined by the noise. It's 1 outside the gap, and the gap is here, and we go to 0 energy, I see a jump to 2. It's actually quite interesting because this allows you to look at pairing. It's even more interesting, this does not even need to be a superconductor. You can also go to a state where you have no superconducting order parameter, but still pairing. So in the limit of high TC superconductors, they are still paired, but the phase coherence is lost. So still you have Cooper pairs, and you can see that. This is a very new paper I have not cited here.
Andreev reflection without superconducting carriers.
Yes. So the carriers are still paired, but they are not in the Bose-Einstein condensation.
Very strange.
Very strange.
Very
Yes,
strange.
very strange. But it has been shown very recently. Yeah. Okay. I should not tell too much because this is all reported and published
So
outside.
why not? But okay, with
So this is
some-
ongoing. This is doubt. This is without any doubt correct. But there are later works from this group where they do this on unconventional superconductors and claim to see pairing without phase coherence. So, but this is a big queue, and with this I will stop my talk a little bit early, but I'm exhausted. And I was fast. So next time I will be a bit slower, but you have to. I have 1 slide less on the next, and 2 slides less on the second next door. So still questions?
Maybe about the final slide, what were those plateaus of noise? Yeah, this guy.
So eventually you have to have a crossover.
But why does it result in a plateau?
You have to look at this paper. This is, I think, the integrated noise. So this is the spectral noise density, and then you can see the step.
Yeah, so it must be somewhere close to the gap where
Yes.
it happens, but
So
it starts even at half the gap.
So this is an infinitely sharp BCS superconductor. In the real world, this has a lifetime, so it's broadened. So you go, there's a region where you have Cooper pair tunneling and single particle tunneling at the same time. Yeah.
I think it's important to say that this experiment has not been reproduced in technicals of conventional supercomputers.
Okay. I don't want to be nasty about this. There's a guy in Milan.
It's just about reproducibility.
There are experiments on planar tunnel junctions that show the same thing.
Oh, that
Yes. So I think this part is not disputed anymore. About unconventional, there is a dispute, but okay, unconventional, the whole story is still under debate. I mean, there are, for example, fast laser pulses.
titanium nitride is conventional.
This is conventional. Yeah, this is conventional. This is not unconventional. Did I say anywhere unconventional? No. This is ordinary. I will go to unconventional.
But how do we know that it was no superconducting coherence? You said that they observe Andrei conduction without superconducting coherence. So how do we know?
Okay. I shouldn't have told this. So I don't have this in my slides here, and I ask you to look it up. I can also look it up tomorrow and give the reference.
Okay.
If it is published already. I've seen it on several conferences, and also spatial mapping of these Cooper pairs, presumably. But let's say there are still disputes, and if I remember correctly, the last author got an ERC grant to actually look at this in more detail. And he's hiring. He hired my postdoc. And let's say things are evolving. I shouldn't. This is all recorded on YouTube. And so talk to the last author, Milan. They are working on this. Actually, quite exciting. If you can see the precursor of superconductivity, the formation of Cooper pairs, but not Bose-Einstein condensation yet. And this has also been claimed to be seen by fast laser pulses in the Hamburg group at the Max Planck. So something is there which is not fully understood. Let's put it that way. It's not my topic. So I'm reproducing papers here. I've never worked on noise. Okay.
Other questions? So it's in this experiment.